Now, in this session, we'll try to understand basically the execution of a file rather on Mac OS. So the Mac operating system makes use of a Macro format, and that's what we are going to understand rather in this particular session. Now, with respect to this Macro format, let us try to see this. This Mac format is mainly used by Mac OS, iOS, and other systems which run the Mac kernel. And when a code is compiled for systems which run with the Mac kernel, the compiled code is organized into Mac or Mac object file format. Now, this file format is used in various types of binary files such as executable, object code, dynamic libraries, and other binary. Now, when I say executable files, these are primarily Mac files that are used to run a program. So when you build a Mac OS or iOS app, the final product is often a Mac OS executable file, which contains machine code that the operating system can execute directly. These files can have a .app bundle, okay, generally for a Mac OS application, or just a binary for iOS application. And they may contain code and resources. So when one runs them, you will see that they are loaded into memory and the program starts executing. With respect to object files, that is .o, these are a result of compilation of a source code. Note that they are not executable fully yet. They contain machine code that is meant to be linked together with other object files and libraries into the final executable. Now, each .o file typically represents one source file's compiled output. And later, the linker will combine these object files together and resolve all external dependencies to produce final executable or a shared library. Further, like when we talk about dynamic libraries, these dynamic libraries generally having like .dylib. So these dynamic library extension, this is the dynamic library extension dylib is used, which contains code and data that can be shared among multiple applications at runtime. So like these are loaded into memory by the dynamic linker. So in Mac, that is dyld, which is a dynamic linker. When an application is run, the dynamic linker loads these all libraries into memory. Dynamic linkers are like shared libraries in Linux, that is .so we know, or a DLLs in Windows. Now, they help us to avoid code duplication by allowing multiple programs to use same library code. Now, the fourth, like when I say other binary resources, mostly they are like bundles. So, for example, you will find that there is maybe a directories. These bundle directories contain executable code, resources, and metadata. Now, they appear as a single file to the operating system. Now, these files are often having an extension .bundle. So a .bundle file is similar to a dynamic library, but is used for specific purposes. Like for example, if you are using a plugin framework, then it would be added there. Now, typical use case for these bundle files is an application about Safari on Mac machines or other softwares which extends functionality via plugins, then you will find these bundle files are used. Now, typically, like this file format, Mac file format consists of following components. Okay, so now these components would be containing header and so on. So, like for example, the first component is header. So which contains basic information about the file, like its architecture, whether it is 32-bit or a 64-bit executable, and its entry point. Load commands would be as a second component. Like these describe how the system should load the file into memory. Now, these load commands contain things like location of sections or segments, text, data, even dynamically linked libraries, and other runtime information if needed. Now you will find that there are segments too. Like segments are large blocks of memory in the file, which may contain multiple sections. So common segments are considered as underscore text, underscore text, and so on. So let us first try to understand how exactly the file is created. This macro file is created, or a macro object file or executable is created. Let us say I have typed this code, okay, which contains, say, some global variables. Okay, I have added one local variable. Now the global variables are, one of them is initialized, other one is not initialized, and third that I used as static int k, it is a static integer which is not initialized. And then the fourth variable that I have is say q, which is a local variable and even is assigned a value. So when I compile that code and generate object code, like by using gcc 1.c-c, it will generate 1.0 file. Now, if I use a file command to find out the type of the file, so I write file 1.0. So it shows me that it is a macOS 64-bit object and ARM64. Similarly, when I use GCC 1.c to generate an executable, so, and if I use again file command with respect to that a.out file, one can see that it shows me now macOS 64-bit executable ARM64. Now, how exactly this file command is identifying that these are the types? So we already know that there are, like, every file contains a header, correct? Now, if I talk about macro particularly, this macro contains major regions, like as I stated, header, okay, the load commands and segments. Now, these segments contain one or more sections, where each section contains code or data of different types. Now, convention to name these segments in uppercase prefixed with two underscores. Okay, like one can see rather in this diagram that there are multiple sections added. Now, for example, if I talk about underscore text, this contains the program's code, that is executable instruction. Further, if you see there is underscore data, this contains program's global variables and other data. And there would be few other sections as well, which would be added there, objc, import, and so on. Now, some of them are referred as sections too. Like these are smaller subdivisions within segments. Okay, like within the segments. So these are the segments that one can see here. And further, it will contain symbol table also if the information is added. The symbol table stores information about, as we know, the functions and variables in the program, like with their names, addresses, and types. And generally, we know that this is useful for debugging, linking, or at runtime also, it would be useful. It also can contain information about dynamic libraries, okay, which macro files use through dylibs, okay, which are kind of shared libraries on Linux. Fine. Now, if at all I want to see that header, I have to make use of a tool called OTool, okay, on Mac. So, for example, to display the header, like I am using OTool as an utility. Now, this OTool is to be used like with the parameter -h, and then your executable file name. So initially, like one may see the file we created earlier as 1.c, I created an object code for it, and then I fired a command called file 1.0. Then it was showing me macro 64-bit object ARM64. Now you may see here, like when I use OTool -h 1.0, it is showing me the header. Now this header contains magic number, CPU type, CPU subtype, caps, file type, MCMDS, size of CMDS, and flags. Now this magic is a magic number for the macro file format. Okay, now you may see the thing that is showed here generally, like is feed FACE or FACF. This is a typical macro magic number. Now the CPU type, this is actually telling you the architecture type. Say in this case, it is 167772228, which corresponds to x86-64. Okay, like currently my laptop is having that particular architecture. CPU architecture. Now, CPU subtype, sometimes it could be the architecture identifier. So, like in this case, it is 0. The file type it shows here is the type of macro file. Correct. So, like one may correspond to object code, two may correspond to an executable file. One can see here when I used it with a.out, like below, like otool-h a.out, you can see that file type is 2 there. Correct. Now, further, like when I see the NC MDS, this is number of load commands that are added. Then size of CMDS, size of those load command in bytes, it is showing. And lastly, the flags. Now, these are the various flags that describe properties of macro file, whether they are relocatable or has some pre-bound symbols and so on. Correct. Now, let us say, suppose if I write this code, I earlier showed the same code to you. So now what we will do is we will try to make use of nm command rather to display the symbols. So I wrote this code. I have again same code is there. Now you may identify here. I defined R, I defined K, but I haven't used either of them. So I used only P and Q. Correct. Now if I display 1.0 with nm, so you will see that there is a main, then there is a P. Similarly, data section, text section, and printf is undefined. Now, whenever you see that a variable is defined, okay, like you have defined it as a global, and like if you see, if you are not initializing that, so ultimately our understanding is that it should be added into BSS. Now, one small change that can be seen here, it goes into common section. Okay. Now you will not identify any thing added for k, which is static integer k, which is static variable uninitialized one. And for r and k is not used by us at all in the code. But still r is added into common because it is a uninitialized variable, a global variable. But static variable which we defined there as integer k is not added at all into this. Simple. Further, if I create an executable and if I generate that executable and I use it with nm, you will see that this is the description that is added there for the symbols along with the addresses. Now, one again can see like each of the address is changing now. Earlier, like for example, as it is a 64-bit machine, this is a 64-bit address, which is compile time address. Okay, this is after linking, the address is changed. So the concept that we understood in the previous video with respect to binding, compile time binding, linking time binding, again can be seen with Mac machine 2. Now let us say what I'm doing is I'm changing so I'm changing the code a bit, okay, here, and let us see that how the output can be seen in different way. Output in the sense with respect to the variables. Now, if I keep the same code like cat1.c as I displayed there, and if I use otool to display data section, you will see that only one variable is added. The way that we saw in earlier slide, only P is added into data section. Okay, one can see same thing over here, like with respect to that particular variable. Okay, like in data section, the number is added. Now, as we are seeing it with 1.0, if I go back and try to see the address for P, okay, it is shown here. So 58, and one can see again it is 58 here, correct? Fine. With respect to now, what I did is to display this data section, I used again otool command, otool utility. So otool dash d 1.0. So it is showing me data section. If I want to see text section, the exact the code, machine code generated, okay, with 64-bit addresses, then one can see this using otool dash d 1.0. Then you would be seeing this. Now, what, as I said earlier, like if I change that code a bit and if I use k now below, like this, say for example, I am still not using r. I have defined p as global, integer r as global, static int k as global. Three of them are used, defined by me as global. one of them is initialized, two of them are not initialized. But now, if I am using this K in my code, rather, okay, earlier it was defined but not used. Now, if I use it, because when I defined it earlier, there was no mention about K in the section. Like here, there is no mention about K when I showed you output of NM. Now, when I use K here in the code, like I added one statement K equal to P minus 10. So you may see here now, this K is added into BSS. Okay, because though it was a static, now again, like if I try to rather see the same code rather, like with respect to 1.0, I would be saying that. So I will show you in a bit. Say, for example, okay, so let me open the terminal. Okay, and let me add say the command. So cd pgm. So this was our code. Correct. So where we used K now, if I compile that code with the to generate an object code. Okay, now if I use 1.0, you can see that this K is added into BSS now. And this is the address that is generated for that variable. Okay, this is a compile time. Now, if I generate executable and if I try to display it with a.out, you will see that this K is added again over here, which is in the BSS section now. This B corresponds to BSS. This U, as we stated, it is rather added as an undefined one. And when you do talk about, like say, for example, S, so if I write NM, man NM, so this S corresponds to symbols in the section other than the other section. So capital T shows you text section. Capital D tells you that it is data section. Capital B probably or small b will correspond to BSS. Okay, and earlier dash C, like we saw C for that variable, which is common for R. Then at the time of execution, like before it was compiled, like before generating an executable, when we see the output of NM with object code, this R corresponds to the common, correct? And then when you create an executable, okay, for a like 1.c, and one can identify here that this R now changed from C to S. So what it does when we see this thing, so earlier C was common symbol, okay, which is used for debugger symbol table entries, okay, but when it creates an executable, when it is not part of data and BSS in executable, while creating executable, it is added into S, okay, symbol in section other than those above. So this is how the information about all symbols can be seen over there. So you can try it for other programs too, and see like how exactly the code is converted into different parts like code section, data section, and so on.